Okay, so yesterday and today morning also, yesterday there was a lot of discussion on MRC, and then those questions came up today morning also. So we have this session from transport to collectives, building an end-to-end communication stack for AI supercomputers with MRC and MSCCL++. It will be presented by Dr. Jithin Jose. He's a partner software engineering manager at Microsoft, where he focuses on communication systems for large-scale AI and HPC platforms. His work includes high-performance networking, transport protocols, collective communication libraries, and the co-design of software and hardware systems for AI supercomputers. He currently leads the engineering efforts in areas such as the multipath reliable connection, MRC, and MSCCL++, AI cluster networking, and large-scale training and inference infrastructure. Prior to joining Microsoft, he held research and engineering roles at Intel and IBM Research. He has published extensively in HPC, networking, and distributed systems, and he got his PhD from the Now Lab group. I don't remember the year, 2014, okay? 12 years back. As I was telling in my talk, with him, I think we started the Hadoop Hadoop over RDMA. I think is Javi here. So he was a postdoc that time. So prior to that, we were purely working on the Rapid RDMA. So we moved to Hadoop, HDFS, the big data. So then you moved to Intel. So I think things are circling back again, kind of thing. So after 12 years, he's coming back. I think you presented some of the AWS cloud stuff in the previous mug also.
Sure.
Azure, sorry. Azure API. So let's give a welcome to.
Yeah, I mean, again, thanks a lot, Dr. Panda, for inviting. It feels so great to be back here at OSU. I still remember like 2013 when we first started. Like, I mean, I was helping with all the stuff like some of you guys do here. So it feels great to be back here and learn all the things, all the great work that has been happening in the group, and also like present some of the work that we have been doing here, right? And again, like here, today I'm talking about some of the updates that has been done by, many of us, people like us, like me, who graduated from here or worked with Now Lab in the previous years. So, in my team, like there are many OSU Now Lab members. So we are working together to make many of these new network transports or collectives happen, right? So today I have two different topics, right? So one is MRC, and then Microsoft Collective Communications Library, or MCCL++. And then finally, we'll talk about like end-to-end, like how, what is the end-to-end stack, and then, what are some of the next set of challenges that we are looking at, right? So again, as we all know, right, communication is one of the key bottlenecks in AI supercomputers, right? And many of the frontier models, right, require 100K plus GPUs to train the workload, right, train the model. And it lasts for quite a lot of days, right? And and they all move lockstep. So, the slowest GPU or the slowest network link defines the actual end-to-end performance, right? So, GPU bandwidth or the network bandwidth is increasingly being the one of the key bottlenecks in the training, right? And similarly, right, like when you look at the training, right, how much percentage of it is actually driven by communication, right? It varies from 10 to 40%, right? So those are all the model, or the characteristics, right? At the same time, right, these clusters, like there may be different training workloads running, or there may be inference jobs running, right? So we need to like support different types of workloads also, right? So, like there could be load balance coming from flow collisions or in-cast issues, like because of the workload characteristics, etc., right? And increasingly, another problem that we see is, so one of our sister teams studied a lot of networking gear, right? So there was a paper, NSDA paper, in the study, like they studied like 180,000 network switches, and most of the faults were actually coming from, like, say, software side of bugs coming on from the switches, right? Which was also, so I mean, the essence is that, like, we cannot really rely on a lot of like optimizations that are from the different networking elements. It becomes extremely challenging at scale to, like, debug problems or, like, find out where the issue is, like, or it may be a feature that may be working negatively, or it may be a bug that is working negatively, etc. Right? So that's a common problem that we are trying to solve. And maybe another point is that, like, so these networks or GPUs, like, move very fast. Like, I mean, so every 6 months there may be a new GPU coming, or network coming. So we need to be ready with the software stack also, right? So I mean, there may be newer models, there may be newer architectures. So how fast can we move to those architectures, and how we can, do the training or inference very fast, right? So, I mean, here, going to the first part, MRC, or multi-path reliable connection, it's an industry collaboration with OpenAI, NVIDIA, Broadcom, AMD, and Intel. I mean, I think, like, Hemel mentioned quite a lot of details in his previous talk, and also in the beginning, like Dan also, Dr. Panda had also mentioned about this, right? So we are not positioning this as this is the answer for all the problems, right? But, like, we are just saying that, oh, this is one of the solutions that we looked at, or that we implemented, and how does it work, right? I mean, like, how is our experience, right, so far, like, for all the, large-scale training, right? And some of the, latest models that you use have been trained using MRC as a backend network, right? Going back to the motivation, right? So, like I mentioned previously, right, network is one of the key bottleneck, right? And again, like, if there are some outliers, right, say one bad link or one faulty switch, right, that becomes a bottleneck. The slowest GPU or slowest networking element defines the performance, right? There can be collisions, like we discussed earlier. There can be multiple different workloads colliding, like in gas pattern, etc. Or there can be, like, silent or noisy failures, right? I mean, trust me, this happens quite a lot, right? So we see switches, dropping packets silently. We wouldn't get notifications, like, so it's very hard to, like, determine those kind of issues, right? And also link flaps, right? At 100K plus GPU scale, link flaps is a normal day-to-day story, right? We have to live with it. Like, we cannot, pause the job, or, like, take care of those. Like, we have, there may be switch servicing that might be that we have to do. So we cannot pause the job, right? And most importantly, because of a network issue, we cannot, it is extremely, cost ineffective to, say, stop the training job, because, Dan mentioned, like, efficiency is one of the key, right? The cost is one of the key, right? So, like, we can always go back to the previous checkpoint, but, like, it comes with a cost, right? So it's, so the network servicing or link servicing, everything, that is a day-to-day routine, right? Another key is operations, right? The clusters are scaling really high, right? But it's the same small operations team, right, who is doing the work, right? So, link flaps or switch recovery, it just becomes a routine thing, and it's not an escalation. It has to happen, like, as a normal event, right? So, what exactly does MRC bring to the picture, right? So so this is actually expanding or extending the ROCE RC protocol, right? And so one of the key principles is that, it's not just specific to MRC, right? Rick mentioned, like, even for IB, like, we are doing multi-plane, right? So the NIC itself, we are splitting into multiple planes. For example, an 800 gigabits per second, like in Fairwater. So we split that into 8 different 8 planes, each with 100 gigabits per second. And the NIC itself, like, each of the plane will be connected to different switches, right? So one NIC will be connected to 8 different switches. And if you have 4 NICs, so one node itself will be connected to 32 different switches, right? So the advantage is that, like, even if, like, say, one link goes bad, my job is not faulted, right? So job wouldn't crash. I can still continue for the time, like, the network is down, like, or that plane is down, like, my bandwidth will be impacted by a little, right? So that's just the multi-plane architecture, and MRC sprays the packet across different planes in a uniform manner, right? So that's first part. And not just, we don't stop just at the plane. We spray the packet at the network also, right? So in MRC, every network packet has an association with an EV, or entropy value. And that EV defines, what's the end-to-end network path that this packet will take, right? So, I mean, it's very, and routing, it's not based on EV. We translate that routing into an SRv6 header. So, IPv6 is SRv6 header. So, so we have an algorithmic mapping that, from this EV, how can we algorithmically prepare this SRv6 header? So that header will be part of the MRC packet. And I'll have a following slide that explains how the packets are traversing through the network, right, or SRv6. Adaptive load balancing, right? I mean, like, from the previous Broadcom talk, right? We heard, like, ECN is used as the congestion signal, right? And then you do the adaptive load balancing, again, like, I mean, reusing the same words from previous talk, right? So we cannot afford to do the go back and protocol, right? I mean, it's very costly for these networks, right? So we do SAC, selective acknowledgement, or NAC, to avoid the head of line stalls, etc., right? Packet trimming is another detail. So whenever we find out, there's a network congestion for a particular path, so you trim that packet, like trim the data out, and then you get the signal back, right, to the source. So now I can select a different EV, so which routes the packet to a different routes, right? So in a gist, that's the, high-level core features of MRC. And we don't stop just at the transport layer, right? So we co-design the network topology, right, with MRC, right? So obviously, we want to scale really high, right? I mean, like, say, for example, if we are, so on the left, we have a single plane topology, like, so we can see that, say, today's switches, right? I mean, 64 port, 800 gigabits per second switches, etc. The max that each switch can support is, I can connect to 32 NICs, each of 100 gigabits per second. And that way, if I connect, so one T0 can connect to, like, say, 32 nodes, and then one T1, right, it can connect to 32 T0s. So each port will be of 1K size. And then at the T2, like, I can connect all the 64 down ports, right? So, so this, even without oversubscription, right, by using all the ports, I can still scale only to a max of 65K GPUs, right? But I mean, we need to scale much larger than that, right? So that's, another motivation here for the multi-plane architecture, right? So with the same switch type, this NIC type, right, with multi-plane, right, we can now, each of the NICs, right, I mean, like, each of the plane will be connected to the NICs. So rather, instead of 65K, I can now scale to 128K easily, right? And still have all the NICs talk between each other, right? And I mean, it comes with a lot of savings also, right? We save on optics, we save on the switch counts, right? Capacity, even like say, even if I lose one of the BT0s, right? Or the first T0 switch, right? So my bandwidth is just impacted by, say, 1/8 or 1/4, depending on how I do the multi-planing, right? And I'm not losing the entire GPU or that node, right? Because the job can still continue. And then quickly on the entropy value, right? We touched briefly on the entropy values. So I mean, just an illustration, right? So here we have a sender QP, and we have a receiver NIC, and these are, like, say, suppose multiple. These are the network end-to-end network links, right? It's not like a direct link. It's just an illustration of, like, end-to-end network path. Suppose so this NIC has 4 planes. Suppose, for example, 800 gigabits per second split into 4. So each 200 gigabits per second, etc. Right? And in each of the plane, right, I can have multiple network paths, right? So plane one may have like 2 pads, plane 2 may have 2, et cetera, right? So, and during the job is running, right? While the job is running, so I get a feedback saying that, oh, one of the network paths in plane 3 is bad, right? So I get that feedback from SAC or NAC, etc., right? So plane 3, that particular EV can be replaced with another EV, which corresponds to a different network path in plane 3, right? And then I can still, so for a very small period of time, I'll see a glitch, but later the job will continue to its peak bandwidth, right? And some of the changes in the reliability aspects, right? So, we don't have to do PFC, right? This lossy Ethernet. Selective retransmissions, like we discussed, again, like packet trimming and ECN for the load balancing, etc., right? We had quite a lot of discussions on like, oh, what should be the routing strategy, right? So can we use BGP or can we use, like static routing based on the EV? Or can we reuse some of the existing industry standard method, right? So eventually we landed on SRv6 based routing. So the innovation was that like, oh, the EV, right, which corresponds to the end-to-end network path, how can we easily or algorithmically map this to an end-to-end SRv6 path, right? So, so we came up with the idea of like a structured IP address and structured UCID assignment. So from an IP address at the source and IP address at the destination, I could build the entire SRv6 path between any pair of nodes, right? For example, this is a very simple example of an SRv6 route. So it will have a locator in the beginning. Say this could be the UCID of, say, the BT0 switch, the first hop. Then it could be the BT1 switch. It could be the BT0 switch at the destination, and it could be the NIC, right? And another case where like, it is under the same BT0. This can be the BT0. This will be the NIC, the target NIC, right? So depending on the topology, depending on the IP address, like I could define the end-to-end SRv6 path, right? One of the key benefits or side benefits that we got with this was SRv6 prober. So now I can find out, explicitly find out or pinpoint where the issue is in my network, right? So, so we have like dedicated SRv6 prober running on every NIC. So that will at times like send these SRv6 based probe messages, and based on the feedback, I can say, oh, this particular link has has some issues or high RTT. Maybe this is on and off, et cetera, right? So it's, we could get like very pinpointed feedback. Also, directly from MRC, we could get telemetry signals that tells me, oh, the similar kind of information, right? Oh, this particular path is good, bad, or maybe silent lows, all those things, right? So it's very telemetry rich, right? And then another, this is a quick, I'll probably speed up a little bit, but so this is one of the job throughput from a production job, right? So when it was running, there was one transceiver flap, and which was corresponding to the BT0 switch, right? And then, so 4 ports flapped for a few minutes, right? It was down for a few minutes. So you can see like, it was 4 different ports of 4 different NICs went down, and that corresponds to like the ports down at the switch, right? So during that time, like we could see there was a small dip corresponding to the bandwidth lost during that time, but the job didn't crash, it didn't halt, like it just continued, right? So that's the thing. And again, like, once, the performance, like latency bandwidth, right? Bandwidth, we get like very close to the line rate, about 96%, etc., right? Line rate, and latency about 5 microseconds, right? Very close to what we typically see with Rocky. Right? And so this is some of the, some of the results comparing how does it compare to Rocky, right? Again, Rocky, as we all know, it can be optimized really well, right? So this is not like the end-to-end, like, or extensively optimized. So, so this compares, right? So, so this one, the dark blue is like when there is no loss, and with 1 QP, like when there is like, 16 QPs, and when there is, this is with MRC with 1 QP, right? So at different loss conditions. So no loss, 1.1% loss, and 1% loss here, right? So you could see, like, even with 1 MRC QP, we could get, really good performance even without any loss, and even when there is loss, it is actually doing much better, right? So that's primarily coming from, like, 1 QP itself uses multiple different EVs, right, to spray packets. So that's primarily it's coming from. Again, like, we can invest quite a lot of time optimizing DCQCN, or, like, lot of the Rocky parameters, like maybe we could improve this. But this was one of the experiments that we did together with all the networking partners, right? And similar story here, like when there is a 7:1 in cast. So this shows the victim throughput, right? So for MRC 1 QP, and for the different Rocky, like plus DCQC and 8 QP and 1 QP, right? So that concludes the first part of it, right? So on MRC. And I'll probably go a little bit faster. So MCL++, right? So MCL++ is Microsoft Collective Communications Library. So the key, like I was describing in the beginning, right? The key challenge for us is that, we have newer models coming in, like, very quickly, right? So OpenAI models are coming, MAI models are coming. At the same time, like, inference architectures, they also move pretty fast, right? So, AMD GPUs, NVIDIA GPUs, right? So we don't have to build quite a big, such big clusters like 100K GPUs scale, etc., for inference, but like smaller scale, right? So this happened very fast. So how soon can we optimize these inference workloads on that particular architecture, right? So, so that's a key challenge that we are trying to optimize. We cannot really depend on, say, generic libraries, general purpose libraries, etc., because they may be optimized on that particular hardware, which may or may not be applicable to our software stack or our architecture, right? So we provide like 3 different layers. So at the very top, like, it's a collective API, right? Applications, or like an least expert user, they can directly use those APIs, like they just call into collectives, already used, etc., like that level of abstraction. And then there is this DSL, or domain-specific APIs. For example, this is primarily like, I think many of you may be already familiar, the PGAS like abstraction. So you write code as if it's on a single node, but like the DSL will automatically separate the kernel. So, what it should run on different GPUs, right, based on the rank, etc., right? And then the last one is primitive API. So we map this to, like, say, based on the underlying hardware or network semantics. Right? So port channel, that is corresponding to, like, say, like RDMA operations, right? Like anything that NIC exposes. Memory channel is something like, say, maybe NVLink fabric, like, again, RDMA semantics there. And the switch channel is something where, like, NVLink sharp kind of features. So, so with these building blocks, right? You can define your collectives very easily. So depending on, like, where the expertise is, right? So we can easily build the different collective operations, and in a very optimized manner, right? Oh yeah, and this is a quick example of the different semantics. Port channel, right? It's put, signal, wait, flush, etc., mapping exactly to the different NIC operations. Memory channel, like put RDMA, write or read, or and then wait and signal, right? And then switch side, where, like, the collective primitives are supported, like reduce or bcas, right? So NVLink sharp, or the NVIDIA sharp, right? And it's a very, very high level, or quick example of how we can write the collective operations using DSL, right? So, I mean, so it's a very small example, like you split the data into like multiple chunks. So you first do the first data. I mean, this is for the reduced scatter, right? So you first, and using a ring. So you first put the first chunk, right, and give signal, right? And then like while you are waiting, right, you do the processing or the reduce operation, the compute operation. And then you wait on the receive. And then like you initiate the communication for the next chunk, etc. Right? So I mean, just showing like how we can write the DSL to do the overlap. And then this is a quick comparison or performance comparison on like so different hardware architectures, how much performance gain that we get compared to nickel or compared to the previous version of MCL, right? So on like NVIDIA architecture or AMD architecture, I mean, the primary advantage is actually coming from the productivity gains, and then like even on the performance, like we are getting much better, right? Speed ups, right? Yeah, again, like connecting it back, right? So the productivity or like how soon we can enable this, right? So that's a key metric. One another thing that I want to call out, like Dr. Panda was also mentioning, the GPNet IO, right? So that's also enabled, right? So we like FGDA or NVSHMEM, like fully compatible. We could see like across the different workloads, we can see like performance improvement or throughput improvement, etc. And then this is another key metric, right? So whenever we have a new hardware, right? I mean, we don't need months of development to make it, get an optimized version, right? So we could be using the DSL or using the primitives, like you can get within weeks, right? Or within like a few days, we can get this going. So connecting end to end, right? So, I mean, so here we have a training and inference workloads. And at the communications library, MCL++ is there, which includes DSL or primitive APIs, nickel or RICL, right? So we have expanded, we have open sourced a MRC nickel plugin, right? Which calls into using the plugin, it calls directly into their different MRC APIs. Same thing like AMD and us, like we are working towards on the RICL plugin or the RICL shim layer. Oh yeah, that's another interesting thing. Like so, we also built a shim layer that's also open source, by the way. What it does is like it tracks any IB words calls, right, and then translates that into MRC. So like out of box nickel or any IB application, like you can work directly over MRC. But I mean, you can like it opens up more doors for optimization when you use the nickel native MRC plugin, etc. Right? So we support both in this case, and as we enable newer NICs like Broadcom or AMD, right? I mean, so those will also be added, right? So yeah, I think that's a quick summary and what we are looking next, right? What are some of the next challenges, right? So MCL++ today is primarily focusing on inference. This has been the de facto library for both, for all the inference jobs in Microsoft, like for both the 1P workloads and also for the OpenAI jobs running on Azure, right? And the MAI ones. But we want to expand the scale, right? We want to include, advanced MRC features, etc. So that's one thing that we are currently looking on. We are always looking to optimize. How can we improve the entropy allocation, like, or coming with some optimizations there, or even like improving the telemetry, like so the operation side can be improved, etc. And then beyond GPUs, like we also want to connect to the storage clusters, right? So that's another area where it's going. And then how we can keep up with the newer hardware, right? So new silicon, how soon can we jump and get it in production, right? So those are some of the key focus areas that we are looking ahead. Thank you. And then the ASPLOS paper, I mean, I have put a link to the MCL++ ASPLOS paper. And HOTAI, next week, we have, there is an MRC, I mean, paper presentation. So Rip from AMD will be doing that. And then the MRC spec is now part of the Open Compute project. And like also put the, I mean, open source links for the different MCL++, the Nickel plugin, and the Shim library, etc. That, thank you. Thanks everyone. Any questions? Yeah.
Thanks, Jithin. We have time for questions in person as well as online. People can unmute yourself or post a question on the chat. Any questions here inside the room? Yes.
Curious about the shim. Curious about the shim library. So verb semantics are different than MRC semantics, right?
Oh.
Like the ordering and all that stuff. So you're reordering everything and the bytes are going.
So yeah, so RDMA write and write immediate semantics are very much similar, right? So that part, so we can support. And MRC currently offers only RDMA write and write with immediate. So that can be supported efficiently. Yes.
Because there's only write, we can do that.
Yes,
Okay.
and now we are like as a 1.1, right? So we are trying to expand to atomics or RDMA read. So yeah.
But if a user tries to, has a mixed application that's not using, it's using other semantics because the writes and the read ordering,
Yeah.
you replaced it, that might be, it might be
Yeah.
have an incorrect
Yes.
application.
Yes,
Okay.
yes, yes. Yep. Good call out. Yeah.
Okay, Hemal, yeah.
Yeah, question is on this MRC Nickel plugin. How extensible that to any other CCLs?
How extensive?
I mean, is it tied to Nickel or you just?
Oh, yeah, it is. It is. So all the higher level part, the algorithm, everything is exactly Nickel. So even Nickel has this different plugin, right? So the RDMA shard plugin is there, or the Nickel when it has a default built-in plugin. So in this case, it's we are just replacing the transport layer.
This is a transport plugin.
Yes. So everything up higher level remains exactly the same.
Okay. Can we make it more general for any CCL plugin? Have you thought about that?
Ideally, yes, right? So maybe if we want to cover all the different CCLs, maybe shim layer.
Yeah, because in my world, Nickel is not the only thing.
Yeah, absolutely. So this Nickel plugin, right? It matches very tightly, or it bonds very closely with the Nickel architecture, right? So I mean, like they used to have this, I mean, architecture for a long time, right? So EFA has their plugin, LibFabric has this plugin, right? So I mean, like Nickel plugins. So that's why for MRC, like Nickel, like we started with that. But yeah, I mean, this is not like, I mean, architecturally, it is not tied to just Nickel. We can, I mean, take the same concepts and get it on others as well.
Okay, thanks.
Norris, yeah.
So for the earlier in the slides, you showed that figure with the error handling and like how the beta flops drop a little bit and then go back again. So what is the algorithm that is used here to like recover the train? It does not look like checkpoint and restarting.
Oh, it is not checkpoint. Like job is not stopping, right? Job is continuing, right? So I just get a feedback on that particular, so in this case, it was a server to BT0, right? So from a server to BT0, I only have one path, right? But let me go back to this slide, right? It's not moving to the previous one, for some reason. Okay, so anyway, so from a NIC, because of the multi-plane architecture, I have, I mean, 4 paths or 8 paths, right? Say, I mean, like if I can do like 2 by 400, all right, or 8 by 100, right? So in this particular case, right, so only, say, one plane was down, right? So in this particular example was a 4 by 200. So, I mean, I lost, say, 25% of the bandwidth during that time, right? And immediately after that plane came back, right? So yeah, my job was able to use that particular plane and then continue the job.
So this recovery happens on the MCR level, right?
MRC level.
Okay, so like there's no need to change anything on the application.
No, application will be completely agnostic, right? So there wouldn't be any completion or error full, right? So if you're referring to that, right? So yeah, nothing.
Thank you.
Okay, so let's then give Jithin a big hand.
Dr. Panda, we had one question online.
Oh, there is a question online. Please go ahead.
I've sent an unmute request.
Yeah, sorry, it takes a second to come off on mute. Jithin, I had a question. You made a comment that that in network, you were not interested in relying on network optimizations because network hardware evolves quickly, and yet you made accommodations for Sharp. So I was wondering, what's your view of in-network collectives and more broadly programmable in-network compute?
I mean, I'm not at all against networking, computing element, etc. I mean, Sharp or NVLink Sharp, like we have seen like quite a lot of improvements, right? But the problem that we have seen is at very large scale, right? I mean, like when we are relying on like say switch specific or network specific protocols, like say for routing, etc., it becomes extremely hard to like debug and find out where the problem is, right? So that's my challenge. But like say, for example, small scale, right, or inference job, right? Yeah, absolutely, it works fantastic, right? So, so yeah, I mean, we would, I mean, and again, I'm not saying that MRC is the answer, right? So, I mean, this is at this time, like, I mean, it is working well for us. But like we will, I mean, we are not like bound to just MRC. Like we are very open to like, or newer technology or like innovations, right? So yeah. Hope that clarifies, Pankaj.
Yeah, okay. So thanks again, Jithin. So we'll switch to the next